x. Could you take the derivative of both of those for us, please?
Yes. So -9 sine 9x for f of x.
Good.
And then 3 cosine 3x over sine 3x.
And then it's kind of up to you if you want to simplify that to 3 cotangent 3x.
Okay.
If you see that. If you don't, that's okay. I don't know. It depends on your instructor if they really think that's important or not.
Okay.
So now it's just a matter of using that in the derivative here. So it's 1 over y prime equals, so be cosine 9x, 3 cotangent 3x plus -9 sine 9x, natural log sine 3x like that. And then you were correct. You do multiply the whole thing by y on both sides here.
Yeah.
Okay, and it's messy. Like this is not a clean, nice looking derivative. We can do a little bit to simplify. It's 3 cosine 9x cotangent 3x minus 9 sine 9x natural log sine 3x. And then these always have that y, which is your original function, sine 3x to the cosine 9x. I guess your teacher doesn't use parentheses in the
Yeah.
problems. Probably should have. Okay. Side point. So that's the answer. Looks like you went the direction of quotient rule or something, but
Yeah. I don't know what I did.
it's okay. I mean, these things are you're stressed. They're not not like a vacation day. So, kind of looking at like, did you do quotient rule correctly? I mean, you did most of it, if not all of it correct, so that's good, but that was, they were looking at the product rule here.
Yeah.
Do you want one like this, or do you want, even if it's not as difficult, or do you want to move on to 11?
I think we can move on. I understand how to do it. It's just I did it wrong.
Okay. All right, rotate left, rotate more left. All right. So this one is one of the indeterminate forms, I believe. It's like
Yeah.
one,
It's
0,
no,
or
it's
no,
the
one.
limit of e.
Oh, you mean it becomes E? This becomes E for the X, I
Yeah.
believe. But um, how to actually do this, where it becomes E, not E to the X. So if you treat this as Y, and Y is equal to 1 plus X to the 1 over X power, you can take the natural log of Y, which equals 1 over X natural log 1 plus X. And if you rewrite that, you get natural log 1 plus X over X.
Yes.
And so this is what you can take the limit of as X approaches 0. So you're really like transforming this problem that you're doing into limit as X approaches 0, natural log 1 plus X over X.
Yeah.
This is 0 over 0 as indeterminate form. So then you remember from here what to do with L'Hopital's rule?
We have to take the derivative of both, right?
Yes.
Okay.
So the derivative of the top is 1 over 1 plus X. Derivative of the bottom is 1.
And
And
then
then you can always go back to trying the value.
yeah.
Like, just keep trying, just keep
So
asking.
it just equal that one equals 1.
That's right. Now, that's the problem though, is that that's not you transformed it. It's that the natural log of y equals 1 because that's the transformation you made here.
Yeah. And we
So
raise
you have to
both to the
solve for
power
y.
of e.
Yeah, use E, so y equals e to the 1,
Okay,
or just e.
that makes sense.
This is a classic textbook problem.
Yeah.
I don't know how you would know this though, if you've seen it before.
Yeah. Okay.
Okay. Would you like, anything else like this one? This would be a little harder for me. I can find one if we need.
I don't think so. I know. I think I'm like really. I feel really confident like doing like the limits and derivatives.
Okay.
It's just I don't even know what happens. Like sometimes I forget to put an X in there, or like silly little mistakes that are my problems. Okay. Can we do like maximum and minimums of like solid figures?
Sure. Um,
I sent you
do we,
pictures from my textbook, but
do you want us to do these or do you want to do more kind of normal problems that these are not normal problems, by the way?
the ones in my textbook aren't.
Yeah, no. Like 19 is kind of one, but um, and we can do them. There's no problem doing them. It's just these are not the standard. Like, I'm
Well,
sorry for always keep asking.
I already did the ones in my textbook for homework, so we could
Okay.
do different ones.
Okay, let me find some. Um,
Okay.
just looking some up here. Um, there's kind of the basic ones you maybe already saw in class, like the product of two numbers. Um, but then like the standard example is the garden problem,
Okay.
something like this. The farmer plans to make a rectangular garden. One side will be against a long barn. Sometimes it's against a stream. He's got a certain amount of fencing that he'll use to surround the other three sides. What are the dimensions of the garden of maximum area? Does this look at all like something you have seen in
Yeah.
class?
Yeah.
Okay. Do you know how to set something like this up?
We have to. I have to use a formula. I have to find the formula.
I would
And
start by drawing a picture.
oh yeah, we got
And
steps. And step one was draw a picture.
yeah, well, yeah, we don't. But the thing here is yeah, the picture only helps you to recognize that there's only three sides. You should always specify what you're maximizing. You're maximizing the area, which is x times y. And then there's always a second equation, which is from the problems here. Problem here is the amount of fencing. So it's kind of like perimeter, but you only have three sides, x plus 2y equals 100. So you always get the equation you're trying to maximize or minimize. And then you always get another equation, or you're supposed to be able to create another equation, which allows you to substitute in. Because you right now to take a derivative of this, you'd have to use implicit differentiation, which you don't want to do. Um,
Yep.
so typically you solve it for y, but not always. It could be x, depends on your problem. Um, but you're saying this is something you've seen before?
Yeah.
Okay, so this is like 100 minus x over 2. That goes into the area equation, x times 100 minus x divided by 2, which is, and then you do want to simplify here. So it becomes 100x minus x squared, and then you divide each of these by 2. So 50x minus 1/2 x
Okay.
squared. Any questions on what we've done so far?
No, and then we take the derivative, right?
Take
Oh, no.
derivatives.
Wait.
Yep.
Okay.
So could you take a derivative of this for us, please?
Yeah. So 50 minus x.
Set it equal to 0. Isn't too bad. X equals 50. Now, depending on the instructor, you're supposed to actually like prove that this is the min or the max
Yeah.
um, with the
We have to do
second
that.
derivative
But we just
test.
point to our Chromebook or into our calculator.
What do you mean by that? Like you graph it?
Uh, well, I just put the equation in. I do. So I put 50 minus, no, yeah, I put 50 minus x, and then I plug in uh 49 because it's 1 under 50, and then 51, and I
Okay,
see if it's positive or negative.
so you're making a sign chart. To do that, though, you're supposed to limit the domain to before you would do that, you would want to limit the domain because it's not minus infinity to infinity. It's well, how much fencing? I mean, if you used all of the fencing on Y, that's I mean that's ridiculous. But I mean, you could or X, But I mean that is what I mean. You see people do that, like really
Yeah.
awkward fences. But it goes from 0 to 100 here is your domain. So
Okay.
yes, you can then test points um, if you want. Like you said, you'll find that this is positive and negative, so it's a max there.
Yeah.
Now, you got to be really careful here. Sometimes the problems ask you for X, sometimes they ask you for Y, sometimes they actually ask you for the maximum area. So you have
Okay.
to be prepared to find all of those things. Like okay, X is 50. Y we said was 100 minus X over 2, which ends up being 25. And then the area is 50 times 25, which is a number I don't have available. 1250 maybe. Um, double check that, please. And then units. You
Okay.
know, I'm units are important because these are the application. But it's kind of like back when you took geometry, like all of a sudden you're like, oh, I gotta, label
Yeah.
stuff. Feet, feet, feet squared.
Okay. Perfect.
Okay. Any questions on that before we move to another problem?
Nope, I'm good on that one.
So there's a small variation on this problem, which is they they'll tell you like the cost of the fencing is $2 on the north and the south sides and $4 on the east and the west sides. Have you seen that?
Yes.
And they'll tell you like this time they have to fix the area. They say they want to constrain like 100 meters squared for the area, but this time they want to minimize the cost.
Okay.
Do you want us to do a problem like this, or do you want us to move on to something else?
Yeah, we can do one like that.
Okay. So these are just the classic problems that you see. So now the cost is you can start, you want to label these sides here.
Yeah.
It's 2x plus 4y plus 2x plus 4y. So the cost is 4x plus 8y. And the area, which is 100, is equal to x times y. So again, typically you get two equations, right? You get the optimization equation,
Yeah.
and then you get a constraint. It's really a constraint equation.
Okay.
So you have to solve that for y. Y is 100 divided by x. And since I just made these numbers up, I don't know if it's going to work out nicely.
Okay.
Uh, we'll find out. Sometimes they do, sometimes they don't. So now you have to be able to take a derivative of this. Could you do that for us, please?
Yeah. Okay. So 4 plus, hold on, negative 800 x the negative 2 power.
Okay, so you set this equal to 0. Could you solve for x for us, please?
Yeah. Square root of 200, which I don't know what that is. Oh, shoot.
Everything okay there?
Yeah. Square root of 200, so 14.14.
Yeah. If you're doing it by hand, they would pick numbers that work out nicely.
Yeah.
This time, if we were to use the second derivative test, okay, the second derivative would be 1600 over x cubed. Then you could then evaluate your result there.
Okay.
And again, you don't have to figure out whether it's what the actual number is. You just know that it's greater than zero, which means that it
Mhm.
is a min.
Okay.
So those are like your classic first types of problems that you'll see. The next one is a distance formula problem. Have you seen
Okay.
that?
Yeah.
Your teacher's doing good, doing real well, giving you these like standard problems. You want us to do this one, or you want me to find some other ones?
Yeah, we can do that one.
Okay. The the thing that's important to remember here is the distance formula. But actually, you can use the distance formula squared because whether you optimize the distance or the distance squared, it's the same
Yeah.
result. And that saves you on your right-hand side from having to take a derivative of the square root.
Hmm.
You can still write the formula though. It's x minus x. Let me do it this way. Let me do it correctly. X2 minus x1 squared plus y2 minus y1 squared. So this is your ordered pair, x1 and y1.
Yeah.
And then minus 0. And then your your y is the function x squared, and your x is x.
Okay.
That's a squared. So to do a problem like this one, you don't expand, although the one on the right here you could simplify.
Okay.
So your derivative on the left is 2d d prime, which doesn't really matter. But on the right here, it's 2 times x minus 3 plus 4x cubed, and you set that equal to 0. So sometimes these are not solvable.
Can't I plug into
Um,
the calculator? Wait. No, I don't think I can. Never mind.
I'm looking at this other solution. Why didn't they? Oh, I made a mistake here. And I'm sorry, that looks okay. Um, the I'm just trying to figure out what to do from here because
Okay.
2x. I picked one that isn't very friendly, so I do apologize. You would um you would probably need to graph this.
Okay.
You would find that when you graph it, wow, it's a really long solution. Um,
It's one.
it's one, yeah. I really picked a bad problem. It's from a Hawaii University. It's like 10 slides to get to the answer.
Oh
Yeah,
my
it ends up
god.
being one. And then you go back and you put that in to find y. Y is also one.
Okay.
And there you get it. So sometimes you do have to use the calculator for that.
Okay.
Okay. Um, Let me go find some test questions.
Okay.
The other variation on the rectangular garden one is the fencing where they add pens. Let me show you this one so you can see this. All right. If you want to build a pen as shown below in the figure of a rectangle with two interior divisions. Uh, you have 1,000 meters of fencing. What is the greatest area you can enclose? So the mistake here is to not label this appropriately. This is X, X, and X, and this is Y. So the area is actually 3x times Y, but
Okay.
the fencing equation, you got a bunch of Y's here. So you
Yeah.
actually have 4Y's plus 6X's equals 1,000 meters.
Okay.
So, and sometimes in textbooks, you'll see like this whole length is X, and then they cut it into thirds. I would not do that. I'd recommend not doing this way.
Okay. And then we solve for y, right?
You can actually solve for either variable. And one of the ones I did earlier, it would have been slightly easier to solve it for X, but you can't go wrong by solving for Y. Like it's going to work out every
Okay.
time. And it's more what you're used to, which is probably also important.
Yeah.
You'll later on in this course you'll integrate with respect to Y, and it's very uncomfortable for students. X, not Y. All right, so this becomes 750x minus 9 over 2x squared. All right, so take a derivative, set that equal to 0.
Okay. So 750 minus 9x,
Okay.
and then equal that to 0. Negative 9x equals 750. 83.333 x equals 8.
Okay, so maybe you stick to some fractions, 250 over 3, and
Okay.
then you could go back in and find Y if you wanted to. You could find the area if you wanted to, and so on.
Okay.
Okay, any questions on that?
No.
All right, so another type of problem you'll see is they'll give you a graph of something like this, like 9y equals 9 minus x squared,
Yeah.
and they'll ask you to maximize the area of this rectangle. But there's a bunch of rectangles. There's actually an infinite numbers, like there's also this rectangle. And
Yeah.
so they expect you to be able to remember the area of a rectangle's base times height. The base is x if you go, left and then right. The base is always 2x.
Okay.
But the height is y. It depends on where you are on there, and they have to give you an equation for that. So
And
in this problem, it would be like 9 minus x squared.
okay.
So this is the area of your rectangle. So once you have that, you can take a derivative, set it equal to 0, so on and so
Okay.
on. Does that make sense to you? I mean, did you see a problem like this in class?
Yeah, we did one of those, but with a cone instead, or a triangle instead.
Okay. Yeah, you maximize the yeah.
Yeah.
So why don't you solve this for us, please?
Okay.
I think it works out nicely.
18 minus 6x squared.
Okay.
6.
Actually, it does not work out nicely, but can you solve that for
Oh.
set that equal? Yeah.
Okay. So square root of 3.
That's actually plus or minus, right? Y equals plus or minus, or x equals plus or minus square root of 3. Because it depends whether you look at it, whether you're going forward or backwards. And
Okay.
again, they could ask you for, X, Y, Y would be 9 minus the square root of 3 squared, which is 6. They could ask you for the maximum area, which is the square root of 3 times 6 or 6 square root of 3. They could ask you for all of that. So
Okay.
be okay with, or be careful not to miss out on.
What they're asking for.
Yes, yes.
Okay.
Um, okay, this is another classic problem. All right,
Okay.
so there's actually a couple of variations on this, but like um, this one says you're standing on the bank of a river that is 1 kilometer wide, and you want to reach the opposite side 2 miles down the river. You can paddle 6 kilometers per hour and walk 3 kilometers per hour while carrying your breath. What route takes you to your destination in the least amount of time? So
Okay.
a couple ways to draw it here. Do you see this as a horizontal river or a vertical river? It doesn't matter. I'm just asking which one you see it as.
Okay. Horizontal.
Okay. So you're here and you want to get you know, somewhere like that, your house there.
Okay.
So the idea is that you can do anything here where you typically know you're going to go diagonally and then you're going to go that direction there. Is
Okay.
that okay? Like that
Yep.
kind of right. So the this is 1 kilometer wide. Um, and then there's a couple of ways to do it where you either call this length X or this X, but the whole length is like 2. It says that somewhere in the problem, 2 miles. I think they meant kilometers. We'll say kilometers there.
Okay.
So let me think about it. So if we call this X and that's 2 minus X right here. So you're gonna swim and then you're going to walk or run with your boat. So you have to calculate D1 and D2. All right. Yeah, I'm sorry. You have D1. We'll get to this next part. So the diagonal distance there, that's Pythagorean theorem. So that's 1 squared plus x squared equals D1 squared. So D1 ends up being the square root of 1 plus x squared. And then
Okay.
you already have this here. So now we want to minimize time. Time is distance equals rate times time. So time is your distance divided by your rate. So your time to go, time in the water plus your time on shore, that's what you're trying to maximize. So your time on the water is the distance, square root of 1 plus x squared divided by your rate in the water, which is 6
Next. Yeah.
plus 2 minus x over 3.
Okay.
And so that's the hard part. Like the optimization problems are all about writing the equation that you're going to optimize because by now you're supposed to be like, oh yeah, I know how to take a derivative, I know how to set it equal 0. I know all those things.
Okay.
Um, the hard part is setting it up. So I don't know if you'll see this problem. It's important that you put X here, not there. Makes
Okay.
it slightly easier, but you get the same result. It's just
Okay. That makes sense.
okay. Um, let's do a can problem.
Okay.
And by none of these are realistic. Like You're never going to be asked to do this because there's other considerations besides maximizing or minimizing things when you're doing
Okay.
this in real life. And
Yeah.
you already know that. Like it's not all about that, but that I mean these are the problems we have. So
Yeah.
okay, so we have a can, beautiful can on the cheap. There's your beautiful can. Let's see your volume. Volume is 1,000 centimeters cubed. Oh, this is important. You want to ask your instructor if they're going to give you the formulas because
Oh
you
yeah, he said
may.
he was. I bribed him.
Good. Um, that's,
The volume of a cylinder is pi r squared times height.
yeah, so I was gonna. I actually tell students to do this all the time. Like go in there and beg that you can use formulas because it's so much easier, and it finally
It is.
worked. All right. So the what I put in the chat there is a nice one-page geometry reference sheet in case you ever don't get the formulas, you'll have them
Okay.
there. So for the cone, sorry, the cylinder, the surface area is 2 pi r squared. No. Yes, 2 pi r squared plus 2 pi r h.
Yeah.
Okay. Couple things. Sometimes your teacher will give you problems like maybe I already saw this in class, like open top.
Boxes.
Um,
Yeah.
boxes, cans. I mean, I don't know. I think that's weird, but that is what they sometimes put into these problems. So that would exclude, like for example, let's say this was like, an open top can, you would lose one of the pi squareds here.
Okay.
Okay. So then the question is always, well, which variable do you solve for up here? And it's generally the linear one, because that
Okay.
substitutes in nicely. So h is 1,000 over pi r squared. So that's 2 pi r squared plus 2 pi r 1,000 over pi r squared. We get some cancellations and no calculus yet. You actually did a bunch of these problems in pre-calculus.
Yeah.
You just ended up using your calculator from this step. You didn't know that there was a thing called a derivative.
I wish I still didn't. It's caused me some problems.
It's big. This is a big deal. I mean, the derivative of points kind of a pretty important thing.
Okay.
Used all the time. All the technology uses derivatives. So from here, derivative is 4 pi r minus 2,000 over r squared. You set it equal to 0. And when you solve for r, you get 500 over pi cube root, like that.
Okay.
If you can get to this step, I mean, you basically are done because you should know how to take a derivative. You should know how to set it equal to 0. And
Yeah.
then you have it. Now that's R. A lot of times you guys don't have any online homework like through WebAssign or
No, we don't.
okay. So like WebAssign, Pearson, maybe you use this before you end up having to go back and like solve for H and then getting the surface area as well.
Yeah.
Right. I mean, those are that's like full coverage of the classic problems that I mean they there are other problems that I can come up with here, but from here they're just weird things. Actually, a student, let me see if he had some problems. I've got some weird ones, I guess, if you want to do something
Yeah, I
different.
guess.
Or do you have other stuff you want us to cover tonight?
No, actually, can we go over 19 on my homework?
Possibly. Let's see what you got.
It's a triangle. It's like the rectangle in like the on a graph,
Yes. Sure.
but
Yeah.
it has
This
like
is
cosine.
that awful cosine. All right, cosine. So this we're trying to maximize the area. The area of the rectangle is base times height. Can you tell me from earlier what the base is in a rectangle problem like this?
Um, X,
X is half of it. That would be the right part.
so
So
2x.
it's 2x, yeah. And the height is cosine x. It's the y value. Like the height is y, but you know what y is.
Yeah.
All right. So now you got to take a derivative of 2x cosine x. What is the overarching rule for that one?
Um, I don't know. What?
Product rules, product
Oh,
rules.
okay.
F and G, yeah. So
Okay.
if you need it, I mean, I think it's good to still come off to the side and write those out. But could you take that derivative for us, please?
Yeah. Okay, so 2 cosine x minus 2x times sine x.
Okay, like that.
Yeah.
All right, so you got to set that equal to 0.
How to
Uh,
do it.
the twos come out. Um, so it's this one's tough. The 2 comes out, so you get cosine x minus x sine x equals 0. You set the inside part equal to 0. So we come off to the left here. Cosine x minus x sine x equals 0. You just move some things around here. You divide by sine x. So you ask yourself, where does x equal cotangent of x? And there's
Okay.
not that many places where that happens. You can always graph.
Okay. Wait, what's the question? So the value of x would just be cotangent x.
It's wherever they're equal, which I was looking
Oh,
here. I does this one, is there a way to know if this is if you have an exact answer or if
Um,
it's
yeah, I can
math?
look at
Because
the book.
it looks numerical to me, but
Number 19. Oh. Um, 1.122 and x equals 0.86.
yeah. So that's what that's where I don't know how you would know that until but you probably graph this and figure out where it equals 0.
Okay.
What I did is I graphed x and cotangent of x and found their intersection here. So that's how you find x. And then to find the area, that goes back into 2x um, cosine of x. Make sure your mode, very important, radian.
Yeah.
You'll never use degree again in math. It's always radian from here on out.
Okay. So 2 cosine x. So should I plug in 0.86 for x
It's
on my
2
calculator?
times 0.86, yes.
Okay.
Cosine 0.86. Make sure it's in radian, and you'll get that 1.122, or you should. Famous last
Oh yeah.
words.
Okay.
So let me give you a problem to try. It's something we haven't tried yet. Okay. Um, so this is an open box problem.
Okay.
and you're cutting out squares from each corner. This is 13. This is 8. Could you come up with a formula for volume of this? Or at
of an
least,
open box. Okay.
yeah.
And we don't know the height.
The height
Okay.
is the corners that you're cutting out.
Oh, okay. So wait.
So you basically have to figure out the new side length and the side length when you cut these out in terms of X.
So isn't it 13 minus x?
That only gives
Times,
you either you're cutting them out from both sides.
oh, so 13 minus 2x
Yes.
times 8 minus 2x.
Yes. Now, where this gets challenging, maybe, is that you are supposed to FOIL this and then
Okay.
multiply by X.
Wait,
Um,
where did the x come from in the front?
height, height
Oh, okay.
for, yeah, height, length, width, if you will.
Okay.
You want to try foiling that for us?
Yeah. Um, so 104 minus 10x plus 4x squared.
I got a little bit different
Mm,
result here.
hold on.
So we got 104 minus 26x minus 16x plus 4x
Oh, so
squared.
negative 36. I
Yeah.
added instead.
Or this is negative 42. Negative 42.
Oh,
And then you multiply everything by x. So it ends up being 104x minus 42x squared plus 4x cubed.
okay.
So again, in like your previous classes, you would have just graphed this and found the max.
Yeah.
Like would have had like a little peak. And you'd be like, okay, there it is. But now you got to take a derivative.
Okay. So 104 minus 84x plus 12x squared.
Yeah, and you set that equal to 0. Now some of these can be solved by hand. I don't think this one can.
We could use our calculator in class, so I'm just gonna use my
Okay,
calculator.
right. So give that
104.
give that a try, please.
Okay. Oh shit, there's two zeros.
You want there's two answers, but they may not both be correct. So there's always a domain restriction.
Yeah.
And in this problem, like you can't fold the box over onto itself. So the domain is actually limited by this one on the right here to 0 to 4.
Okay.
And that's kind of instructor specific. They're going to be very, challenging like that. But this,
Okay. 1.607.
and then you could take the second derivative if you wanted to prove that it was the max, or you could make the sign chart.
Yeah.
It's up to you.
And then figure out the max. That works. Would you like me to do that or?
No, you don't have to do that. I'm
Okay.
just looking for some more problems here. Uh, running out of time a little bit here. Let's see what this one was. Um, I don't know.
Give it
Do
to
you have any other?
entries here.
Yeah, do you have any other?
No.
Yeah, okay. I don't know. We can stop there. All right, stop the recording.